welcome to the lecture course CH-102 Organic Chemistry for F.Y.B.Sc class. So in last lecture we have discussed interconversion of projection formulae. In that we have discussed interconversion of Sauer's formula into Newman projection formula. Also we have discussed interconversion of Fisher projection formula into Sauer's formula. So in this lecture we have discussed about conformational isomerism in ethane molecule. So firstly, conformational isomerism in ethane molecule. So stereoisomers are classified into two types, with the configuration and conformation. Conformational isomerism further classified into two types, that is the for cyclic and acyclic molecules. So in this lecture we are going to discuss here conformational isomerism in ethane. Before that, you must know the definition of conformational isomerism. So conformational isomerism is nothing but different arrangement of atoms that can be converted into one another by carbon-carbon single bond rotation is known as the conformational isomerism. Conformational isomers, and this phenomena is known as the conformational isomerism. So what is the definition? Different arrangement of atoms that can be converted into one another by carbon-carbon single bond rotation is known as the conformational isomer, and this phenomena is known as the conformational isomerism. So conformational isomerism definition: different arrangement of atoms that can be converted into one another by carbon-carbon single bond rotation is called conformational isomer, and this phenomenon is known as this phenomenon is known as conformational isomerism. Okay. For example, in ethane. Okay. Example, ethane. Then N propane. Then N butane. Okay. So conformational isomerism have the same structural formula but different arrangement of atoms or groups in the space. Is nothing but conformational isomerism. So in acyclic molecules, in ethane, propane and in butane, carbon-carbon single bond free rotation. Because of that, different arrangement of atoms or group in space we can observe. So we get the different conformation. So that is nothing but conformational isomers. So in this lecture we are going to discuss a conformational isomerism in ethane molecule. In ethane. So with the help of model we can consider that this have the two carbons This model contains 2 carbons and each carbon carries 3 hydrogens, 1, 2, 3, 1, 2, 3. Okay. So this ethane molecule present in 2 conformation. First is eclipse and second is the staggered or also called anti-conformation. So this model is the eclipse conformation. If you rotate the one carbon by angle 60, how much angle? 60 angle. So we get the staggered or anti-conformation. So we rotate along carbon-carbon bond and we keep one carbon fixed and we rotate the one carbon by angle 60. We get staggered conformation. Okay. This is angle 60. Overall angle is the how much? 360. So we rotate the by angle 60, we get the which conformation? That is the staggered conformation. So for our distinguished purpose, suppose we consider here suppose our purpose, suppose our convenience purpose, suppose I consider here this is the not any group, this is also hydrogen. For distinguished purpose, I consider this is the I take here this kind of group here. So this is eclipse conformation. By angle 60, we get the staggered again by 60. So we get the again eclipse conformation. So we get the 60 staggered, again 60 we get the eclipse. Means at angle 0 eclipse. Okay. Angle 0 we can observe eclipse. Staggered 60. Okay. Staggered 60. Then again eclipse for angle 120. How much rotation? From this to this, that is the 120. Means from this position, means for this, suppose I consider this group, from this to this, so how much? That is the 120. Again 60 rotation, so we can observe through to this means overall 180 angle. How much? 180. For this also we observe the staggered conformation. Okay. Again 60 means for angle 240 overall, we can observe the eclipse conformation. Then 300 for this also staggered conformation. Here 300 degree overall, and again 360. That is the eclipse conformation. So from this model we can conclude that eclipse conformation in ethane 0, 120 to 14, 360. For this angle we can observe the eclipse conformation, and staggered 60, 180 and 300. For this angle we can observe the staggered conformation. So firstly, when you consider the ethane molecule ethane contains 2 carbons. Okay, this molecule we are going to write here in this source formula. First, source formula is H and H. So this is the source formula. Suppose this is HA, HB and this HC. HD, HE and HF, like this. So first, this is source formula, and this source formula for eclipse conformation. So first consider its Newman projection formula, Newman. So how to write Newman, you know that very well. Okay. So this is the HA, HB and HC. Okay. Suppose this is the carbon 1, this is the carbon number 2. You know that very well with the help of model. So this HA, HB and HC, this is the front, this is the back carbon, that is HD, HE and HF. So like this we can distinguish. So this is the this is the Newman projection formula and eclipse conformation. Which conformation? Eclipse conformation. So our molecule exists in this conformation, eclipse. So HD, HE and HF like this. So this first conformation is possible for this molecule. Now the second conformation, if you rotate this carbon, rear carbon by angle 60, for that we can observe this conformation, staggered conformation. By angle 60, HD, HE, HF, okay, angle 60 rotation. So this is the second conformation that is possible for this molecular staggered conformation. Staggered conformation. So eclipse and staggered conformation. Eclipse angle 0, diagonal angle 0, 120, 240 degree and 360. For this angle we can observe the eclipse. Then 60, then 180 and also 300 angle we can observe staggered conformation. So what is the diagonal angle? So diagonal angle is nothing but angle between two non-bonded hydrogens or two non-bonded group is nothing but diagonal angle. So diagonal angle is changed from 0 to 360 during the carbon-carbon single bond rotation. So this is overall is the 360. Overall angle is 360. So diagonal angle is changed from 0 to 360 by carbon-carbon single bond rotation. Also diagonal angle is nothing but angle between two non-bonded hydrogen atoms or groups. See here, this group. So what is between these two groups? That angle is nothing but diagonal angle. Okay. So here diagonal angle is 0. After this become 60. Then again from this to this diagonal angle is a 120. Then again 180. Then 240. Then 300 and again 360 like that. Diagonal angle change from 0 to 360. So here our molecule exists in two conformation, eclipse and staggered means anti-conformation. So for angle 0, then 120, 240 and 360. For that we can observe the eclipse. And for angle 60, then 180, 300. For that we can observe staggered. So here we are going to consider a molecule in Newman projection formula. We are going to consider molecule in Newman projection formula firstly. So this is the angle 0 diagonal angle and this is the eclipse conformation. What we call eclipse conformation. So we consider our ethane molecule in Newman projection formula, and this is the diagonal angle 0. That time, so for our convenience we take this group here, not this group, but for distinguished purpose we consider this type of situation. Diagonal angle is 0. So we consider the same molecule into the Newman projection formula. Okay. So angle 60 means carbon-carbon single bond C1 C2, that bond undergo free rotation, and we have to keep one carbon as it is, and we have to rotate one carbon by angle 60. Suppose if you rotate back carbon by angle 60, suppose in this direction 60 angle, so we get the conformation like this. Newman projection formula we can write like this: H. Okay. So this hydrogens, back carbon hydrogen, we can write like this. This angle is 60. How much? 60 degree. So staggered conformation. What do you call staggered conformation? Okay. Staggered 60 degree. Again, if you rotate by angle 60, so how much? It is overall 120. That time this become again how much? Like this, real carbon hydrogens, we can show like this. Real carbon hydrogens. So this hydrogen come to this position by angle 120. This is the eclipse, and angle is 120. Okay, this is the stagger at 60 degree, 120. Again angle 60. So overall become 180 angle. So how much angle overall? 180. That angle so like this 180 angle, 180 degree. So that is the nothing but staggered conformation. Staggered. What we call staggered conformation. Okay? Like this situation. Again angle 60. Overall become 240. That is nothing but which conformation? Eclipse conformation. Angle 240. So this become overall 240 degree angle. That is the eclipse conformation. What we call eclipse. Eclipse conformation 240. Again angle 60. So overall angle become 300. That is nothing but staggered conformation. Here, this is the staggered conformation. If you view like this, this is nothing but staggered conformation. So this angle is 300 overall. So this hydrogens that is nothing but staggered conformation. What we call staggered. And after again 60, that is nothing but 360 overall, means 360 like this. So 360, this is nothing but eclipse conformation. Okay. 360 means overall this come at the original position by angle 360. So this is the eclipse conformation. So from this we can conclude that for angle 0, then 120, then 240 and then 360 means for angle 0, then 120, 240 and 360. For that angle we can observe eclipse conformation and staggered conformation, 60 angle, 180 and 300. For that angle we can observe the staggered conformation. So in this way we can show the conformation isomerism in ethane molecule. Firstly, we are going to talk about the conformation isomerism in ethane molecule in that eclipse conformation. Firstly, we are going to talk about the eclipse conformation. Eclipse conformation, in that conformation, the hydrogens on neighboring carbons means non-bonded hydrogens. That non-bonded hydrogens are maximum close to each other in which conformation? In eclipse conformation. See here, in this conformation, that is the eclipse conformation, we can observe the non-bonded hydrogens that is maximum close to each other in this conformation. And this conformation we can observe for angle 0, 120, then 240 and 360. For that angle we can observe the eclipse conformation. And this conformation is a more energetic conformation than staggered conformation. So this conformation have the energy 3 kilocalorie per mole. So here actually eclipse conformation, in that this conformation have the energy 3 kilocalorie, means here this hydrogens, these two neighboring hydrogens are show the interaction. So this shows eclipsing kind of interaction. So each hydrogen's eclipsing interaction is a 1 kilocalorie per mole. How much? 1 kilocalorie. So this contains how much? 3 interaction H. So overall 3 kilocalorie per mole. This much energy we can observe for eclipse conformation. So eclipse conformation is the more energetic and less stable conformation, and less preferred conformation also. So this is about the eclipse conformation. And also in eclipse conformation, this carbon hydrogen along this electron is present, carbon hydrogen, also this carbon hydrogen along this electron is present. And when these hydrogens are maximum close to each other, they show the repulsion between these two. Means non-bonded electrons are repelled to each other. So this electron and this electron along this bond, these are repelled to each other, and so because of that repulsion. So we are called that repulsion is nothing but torsional interaction. Non-bonded torsional interaction we can observe for eclipse conformation. So for this conformation we observe the non-bonded torsional interaction. We can observe. So because of that we can observe energy 3 kilocalorie per mole. So this is about the which conformation? That is the eclipse conformation. Second is the staggered conformation, 60 angle, then angle 180, then angle 300. For that we can observe staggered conformation. So in staggered conformation we can observe that non-bonded hydrogen, they are maximum apart from each other, and when they are maximum apart from each other, So this conformation is the more preferred and more stable conformation, and this have the energy only 0 kilocalorie per mole. Means in this conformation we cannot observe the torsional interaction. Means non-bonded torsional interaction we cannot observe. Why? Because of these non-bonded hydrogens are maximum apart from each other. So this is the more stable conformation. So this is the staggered conformation. So this is about the staggered and eclipse conformation. So from this conformation isomers by rotation angle 0 to 360, we can draw the potential energy diagrams here. So energy profile diagram we are going to consider. So in this diagram we plot the graph potential energy of the molecule in kilocalorie per mole versus dihedral angle So potential energy we can draw on x-axis, dihedral angle we can draw on y-axis. So in this way angle dihedral angle 0 then angle $60, then 120, then 180, then 240, then 300, then 360, like this. So like this diagram we can draw. So when we consider this type of graph, or x-axis potential energy and or y-axis dihedral angle, so how the potential energy of the molecule is changed by carbon-carbon single bond rotation. So for 0 angle we can observe the energy 3 kilocalorie per mole. I have told that this eclipse conformation of the energy 3 kilocalorie, while staggered conformation of the energy only 0 kilocalorie conformation. Staggered conformation 0 kilocalorie per mole, and this have the 3 kilocalorie per mole. That is eclipse conformation. Okay. So angle 0, 3 kilocalorie, then angle 60, staggered conformation. That time energy 0 kilocalorie per mole. For angle 120, staggered eclipse conformation 3 kilocalorie per mole. And angle 1 is staggered conformation, that is the 0 kilocalorie per mole. So in this way we can plot the graph potential energy versus dihedral angle. So with the help of dihedral angle, how the energy of the molecules changes. So from this graph we can conclude that energy barrier between two conformations is only 3 kilocalorie per mole. And also we can conclude that staggered conformation is the most stable conformation, while eclipse conformation is the least stable conformation. So staggered conformation is a more favorable and preferred conformation. And also we can conclude that here kinetic energy of the molecule is always 20 kilocalorie per mole. How much? Kinetic energy of the molecule is 20 kilocalorie per mole. So like this much energy we can observe for any molecules, kinetic energy of the molecules. So the energy value is only 3 kilocalorie per mole, and from that we can conclude that our molecule is continuously changes into two conformation, that is the eclipse and staggered conformation. Only energy value is 3 kilocalorie, and also because of that we get this type of graph. So because of that we can observe this type of graph. So means in our molecule carbon single bond free rotation observed at even ground state. So in this way we can observe the things from energy profile diagram. So this is all about the conformational isomerism in ethane molecule. In next lecture we are going to discuss about the conformational isomerism in N-butyl molecule.